Hello everyone. So we have a mid-semester exam past paper here for UNLAS, which is a PMRCH 110, okay, chemistry, okay, for 2024. So we'll learn through the MCQs for this particular past paper, okay. So I'll start with my first question, which is question number 1. Okay, so here question number 1 is saying, what is the best answer for the following problem? So we've been given a problem there, which you have 4.125 plus 0.530 plus 71.4. Okay, so you're adding these numbers. Okay, so what concepts do you need to know here? So when you are adding or subtracting numbers, okay, so you leave your final answer depending on the least. So you follow the least decimal places. Okay, when you are adding or subtracting numbers, okay, when you are multiplying or dividing numbers, you follow the one with the least significant figures. Okay, so this is the concept. So now here we are adding these numbers, these three numbers. So we follow our final answer should follow the one with the least decimal places. Okay, so here we can see that we are having this first number with the 3 decimal places. This one also has 3 decimal places. Okay, and then this one has 1 decimal places, 1 decimal place there. Okay, so meaning our final answer needs to have 1 decimal place. Okay, so when we add these 3 numbers, we are getting 84.055. Okay, so we need to round off this number to 1 decimal place. Okay, so here that's where our 1 decimal place is going to be. So you have 84 point, so you have a 0 and there's a 5, so you can simply add the 1 there since it's a 5. Okay, so you can add the 1 to a 0, meaning you have 84.1 as the answer. So there the answer is B. Okay, so we can go to question number 2. So question number 2 say what is the symbol of the species that has the proton number? So the proton number there is 16, and the electron number of 18. Okay. So now what you need to know for a neutral atom, or for an element which has not lost or gained any electrons, the Z number, which is the proton number, is equal to the electron number. Okay. So this proton number is equal to the electron number when this element is a neutral element which has not gone any chemical reaction. Okay, so a normal element. Okay, so now for this element, it will try to gain stability by either losing or gaining electron. So the electrons are the ones which are going to take part in that chemical reaction, because they are the ones which are going to be involved with the gaining or losing for a chemical reaction to happen. But the Z number remains unchanged. Okay, so now here you can see that we're having a proton number of 16. Then the electron number is now 18. So meaning for this species, what has happened is that it has gained 2 more electrons. Okay, so it has gained 2 more electrons. Okay, so when a species is gaining electron, means that it becomes negative. Okay, so here you have a charge of 2 minus. Okay, so if you check on your periodic table, okay, you find a species with a proton number of 16, definitely you're going to get sulfur. Okay, so your sulfur will have a proton number of 16. Okay, now when it loses 2 electrons, you find that it will have a 2 minus sign there. Okay, so there the answer is going to be C. Okay, so we go to question number 3. So let's go to question 3. So question 3 say how many milliliters of ethanol are needed to prepare your 500 milliliters of a 3.5% volume by volume ethanol stock solution. Okay, so you have your 3.5% volume by volume of your ethanol stock. Okay, so this means that you have 3.5 milliliter of your ethanol, which is a solute, okay, divided by, so you also in 1 milliliter, 100 milliliter of this solution, okay. That's what this percentage volume by volume mean, okay. So you have your 3.5 milliliter of your ethanol in 100 milliliter of your solution, okay, for your solution. Now, we've been asked to find the volume, which is the milliliter of ethanol. So you are being asked to find. So this should be equal to the volume of ethanol, which is your solute at this volume, okay, of the solution which it was prepared there, which is 500 milliliter. So what of at 500 milliliter? Okay, what are you going to have? So you can now calculate solve this equation. So you cross multiply there. So you have 100 times x, which is giving you 100x is equal to, then you have your 3.5 times 500. Okay, so I have my 3.5 times 500 milliliter. Okay, so here I can simply divide both sides by 100. Okay, so here my x is equal to, so this will go, so I have 3.5 times 5. Okay, so if I do my 3.5 times 5 there, I'm going to get 17.5 milliliter as my volume. So there the answer is A. Okay, so you can proceed to question number 4. Okay, so question number 4 saying heme obtained from red blood cells bind oxygen O2. Okay, how many moles of heme are there in 75 cubic centimeter of your 0.0119 molarity of heme? Okay, so you've been given the concentration of heme there. Also, how many millimoles? So you have millimoles of heme are there in 75 cubic centimeter of your 0.0119 molarity of your heme solution. Okay, so here you know that for us to get the number of moles, okay, so you know number of moles, okay. So you have the concentration here. So if you relate the mole concentration and the number of moles, you know concentration is given by number of moles divided by volume. Okay, so I can make my number of moles subject to the formula there of concentration times volume. Okay, so here I've been given the concentration, okay, which is the molarity there, which is 0.0119 molarity. Okay, this is the same as mole per liter, okay, times the volume. Okay, so what volume have I been given? I've been given 75 cubic centimeter. So what I need to do is to convert this cubic centimeter to liters. Okay, so that I have uniform units there. So I have liters here. So I also need to have liters there. Okay, so for me to convert my cubic centimeter to liters, I'll use my conversion factor. I know that I have 75 cubic centimeter there. Okay, I multiply with the unit conversion factor. I know that my 1 cubic liter, or my 1 cubic decimeter, which is the same as 1 liter, is equal to 1000 cubic centimeter. So that my cubic centimeter and cubic centimeter there will go, I'll remain with the liters. Okay, so I simply divide my 75 by 1000 for me to get my volume in liters, which is 0.075 liters. Okay, so this is my volume in liters. Okay, so there I can calculate my number of moles. Okay, so I multiply there, I'm going to get 0.0008. Okay, so 0.0008 925 moles. Okay, so these are my number of moles. So we've done the first part, which is to calculate the number of moles. Now they're asking us how many millimoles. Okay, so millimoles is indicated by M mole. So this means millimoles. Okay, so all we need is to do here is to convert this 0.0008 925 moles to millimoles. Okay, so we'll multiply with the conversion factor as usual. Okay, so I know for me to come up with this, I know that one. Okay, so one more. So one more is giving me okay, is giving me 10 to the power 3 now 10 to the power 3 millimoles there. Okay, so one more is giving me 10 to the power 3 millimoles as my conversion factor there. Okay, so here I can this more and the more will go, so meaning I'm multiplying this with times 10 to the power 3, which is 1000. Okay, so there when I multiply with 1000, I'm going to get 0.8925 millimole. Okay, so the final answer there is going to be 8. Okay, so that's my answer there, 8. Okay, so can go to the next question, which is question number 5. Okay, so question number 5, being given, they say how many liters of chlorine gas. So how many liters of chlorine gas, which is CO2, okay, can be obtained from at 40 degrees Celsius temperature and at a pressure of 787 millimercury, okay, from 9.41 grams of your hydrochloric acid. Okay, so they are saying the chlorine gas is produced according to the equation. So being given this equation on how the chlorine gas is produced, where you're getting your paramagnet there reacting with the hydrochloric acid to give you water and potassium chloride and manganese chloride, and also chlorine, your chlorine gas there, which you are obtaining. Okay, so now they're saying we have to calculate the volume. Okay, so here we have the we'll apply the ideal gas equation to get the volume. Okay, so you know that PV is given by the ideal gas equation. PV is given by nRT. Okay, this is the ideal gas equation. So we are trying to get volume here. So you can make volume subject to the formula. So here volume is equal to nRT divided by P. So I've simply made a volume subject to the formula there. Okay, so now I have my rate constant. I know the temperature, which is 40 degrees Celsius. Okay, I don't know the number of moles. Okay, I have the pressure. The pressure being given, which is 787 millimercury. Okay, so what I need there is the number of moles. So the number of moles for what? For our gas here, because we are calculating the volume of our chlorine gas. So let's get the number of moles for chlorine gas. Okay, so number of moles, you know, it's given by so number of moles, we know that it's given by mass divided by molar mass. Okay, divided by molar mass. Okay, now here in the question, we've been given the mass for hydrochloric acid. We haven't been given any information on the product there, which is the chloride. Okay, so when you are dealing with more concept and you are given information on one or the reactants, just know you consider that reacting to the limiting reactant. Okay, so in this case, they are simply telling us hydrochloric acid is the limiting reactant. Okay, so this limiting reactant is the one which is going to help us get our number of moles. Okay, so here we can simply get the number of moles for your chloride. Okay, so we get the number of moles for your chloride gas by using the mole ratios. Okay, so you get the number of moles for your hydrochloric acid. Okay, and then I multiply with the mole ratio for these two, okay, the chlorine and the hydrochloric acid. So I know that 5 moles, so I'm getting the coefficient. 5 moles of your chlorine is giving you 16 moles of your hydrochloric acid. So I'll simply multiply the number of moles for my hydrochloric acid by this ratio, which is 5 to 16. Okay, so there I can get the number of moles for my chloride gas there. Okay, so the number of moles for hydrochloric acid. So how do we get them? So we've been given the mass. Okay, so we simply say number of moles for hydrochloric acid, okay, be equal to mass divided by molar mass. Okay, so the mass there is 9.41 grams, okay, divided by the molar mass for your hydrochloric acid. Okay, so you get your molar mass for hydrochloric acid, which is for sodium, okay, you get your 23 plus your 1 there. Okay, so I can simply say 24 plus 35.5. Okay, so you use according to what you have in on the periodic table. Okay, so you get the molar masses for these two guys. Okay, which is the 23 for your okay. So made a mistake, so it's not sodium, it's hydrogen. Okay, so hydrogen is going to be 1, so I'll just get 1, but you use 1.008. Okay, then times the molar mass for my chloride, my chlorine, which is 35.5. Okay, so here I divide these two. Okay, so I'm going to get the molar mass there will be 0.25811. Okay, then I multiply with my my mole ratio there, which is 5 divided by 16. Okay, so I simply get the number of moles for my chloride gas. Okay, so remember what I'm trying to do here is to get the number of moles for my chloride gas so that I use them to come up with a volume for my chlorine gas. Okay, so there the number of moles, if you get your 0.255811 times 5, then you divide by 16. Okay, you're going to get 0.0, okay, so 0.08066 moles. Okay, so these are the number of moles, 0.08066 moles. Okay, so I can now simply put in my equation there. So I have the number of moles, which is 0.08066, okay, times the molar mass, the rate constant I'm going to use is 0.0821, okay, then times the temperature. Okay, so temperature have been given 40 degrees Celsius. Okay, so I simply add 273.15, okay, to get my temperature to Kelvin. So you use this temperature, you convert it to Kelvin by simply adding 275. Okay, so you get your 40 plus 273.15. Okay, so this will give you your temperature in Kelvin. Okay, so here I'll get my temperature in Kelvin to be 318.15. Okay, Kelvin as my temperature. Okay, then I divide by the pressure. So here again, I convert this pressure to atmospheres. Remember, this rate constant is having units of liters atmosphere per mole Kelvin. Okay, so I have to convert this temperature, which is in mercury, millimercury, to atmospheres. So I use my conversion factor. Okay, so I know here 1 atmosphere. Okay, so I've been given my 787 there as millimercury. Okay, then I convert this to atmosphere. So I know that 1 atmosphere is giving me 760 millimercury. Okay, so there I simply divide these two, I'll get my pressure in millimercury. Okay, so if I divide my 787 by 760 there, I'll get my pressure in atmospheres would be 1.03 atmospheres. Okay, so that's my temperature in atmospheres. Then I divide there, I'll get my final volume, which is 1.99 liters. Okay, so this is what you do when you ask such a question. So there, the answer is definitely B. Okay. So we go to the next question, which is question number 6. Okay. So question number 6, I'll solve it in form of a table. So I use a table to solve question number 6, saying this guy who is a substance. Okay, so we have putrescine is a substance produced by decaying animal, and as the empirical formula. So being given the empirical formula for this guy, which is this one. Then several determination of the molecular weight give values in the range of, so being given the range of the values for the molecular weight, which is 87 to 90 atomic mass unit, okay, or grams per mole. Okay, so find the molecular formula for this guy. Okay, so we have to find the molecular formula for this guy. Okay, so the first thing you do, you know that you've been given the empirical formula, which is C2H6N. Okay, so this is the empirical formula. Okay, so for you to come up with the molecular formula, you know that you need to multiply this with N, and N is given by, so you get the molar mass for your molecular formula. So the molar mass of the molar formula, your molecule, so you get the molar mass of your molecule or the molecular formula, then you divide by molar mass of your empirical formula. So this will give you delta N. Okay, so in this case, we need to come up with the molar mass, okay, of our molecule. Okay, so the molecular mass for this compound, so we've been given the molecular mass in the range of 87 to 90, okay, atomic mass unit. So we can use any of these in that range. Okay, so you can use any, so you can use 87, 88, 89, and 90. So you choose any of these. You use any of these to as your molecular weight there. You can also use the average of these if you want. Okay, so you get the average of this, then you use it. Okay, so since it's within this range, I can choose any of these numbers. Okay, so I've decided to choose 88 there. Okay, so I have my molecular weight to be 88. Okay, then this is grams per mole. Okay, then I get the molar mass for the empirical formula. So the molar mass for empirical formula, so you get your 2 times, so this 2 times 4.01. By now, we should be able to know how to come up with a molar mass for anything. Okay, so here, hydrogen, I have 6 hydrogens times 1.008. Okay, then nitrogen, okay, so I get my 14, okay, times 1 there. Okay, so I add these. Okay, so I'll find my molecular formula to be 44.8 grams per mole. This is the molar mass of my empirical formula. Okay, so I divide those two, I'm going to get a 2 there. Okay, so I'm getting a 2. So the value of N is 2. So from there now I can come up with the molecular formula. Okay, so I simply, where there is n, I replace it with a 2. I found the value of n to be 2, so I replace it with a 2 there. Okay, so I have C for H. Okay, so 2 times 6 to be 12, then N2. Okay, as my empirical formula. So there, the answer is B. Okay, so we can go to question number 7. Okay, so we can go to question number 7. Question number 7 say, what is the partial pressure of nitrogen in the container that contains 2 more of oxygen, 3 more of carbon dioxide? So we have 2 more of oxygen, 3 more of carbon dioxide, and 3 more of nitrogen, when the total pressure is 800 millimercury. Okay, so here you've been given this number of moles. Okay, so you have 2 moles of oxygen, 3 moles of carbon dioxide, and 3 moles of nitrogen. Now, we've also been given the total pressure. Okay, so we've been given pressure total, okay, which is 800 millimercury. Okay, so what we need here is to find the partial pressure. Okay, so you know that partial pressure, okay, so partial pressure, in this case, you are finding the partial pressure of nitrogen. So I can say partial pressure for nitrogen is going to be given X. So this X means that I have the mole fraction. Okay, so I get the mole fraction for nitrogen, okay, times the total partial pressure, okay, which have been given there. Okay, so I have my total partial pressure. So what I need is the mole fraction of my nitrogen. Okay, so how do I get mole fraction? So mole fraction is simply you get the total number of moles. Okay, so I'll get my total number of moles. Okay, I get the number of moles for nitrogen, then I'll divide with the total number of moles for this container, which are in this container. Okay, so the total number of moles which are in the container are these ones. So you have my 2 plus 3 moles of carbon dioxide plus 3 moles of nitrogen. Okay, then the number of moles for nitrogen in the container is 3. So the mole fraction for nitrogen, so I simply get my 3 divided by, so here I add 2 plus 3 plus 3, which is 8. Okay, so I'll get my mole fraction there. Okay, so there, when I divide 3 by 8, I'm getting my mole fraction to be, okay, so this would be 0.375. Okay, then I multiply with the total pressure there, okay, which is 800 millimercury. Okay, so I multiply there, I'll find the partial pressure for nitrogen to be 300 millimercury. Okay, so there the answer is A. Okay. Okay, can go to the next question, which is question number 8. Okay, so question number 8 saying which of the following is a D block element? So which of these elements are D block? Okay, so I can pick 2 elements which are D block elements. Okay, so your AU there, your got, and your zinc there. These are D block elements. Okay, so there are 2 answers there. B and D, they are D block elements. Okay, so that one straightforward. You just go to your periodic table, you check on the transitional methods, you find these 2 elements as D block elements. Okay, so you can go to question number 9. Okay, so question number 9 saying the following postulates form the kinetic molecular theory, except, so which one does not form the kinetic molecular theory? Okay, so which one does not assume the kinetic molecular field. Okay, so let's start with the first one. So first one, say all collisions are elastic so that the molecule bound off each other and the total kinetic energy stays the same. So yes, so kinetic energy does not change. So the kinetic molecular theory will assume this, okay? So that one is true. So it's not an exception. Okay, so in this case, it's not an answer. Okay, so it's not an exception. So this one, it's not an answer. Okay, then they're saying B, they're saying uh, the molecule in a gas are in continuous motion. Yes. Okay. So this one is also true about the kinetic molecular theory. So it's not an exception in that case. So it's not an answer. Okay. So we go to part C. So part C is saying there are no intermolecular forces. So the only interaction between the molecules are collisions. Yes. So also that one is also part of the kinetic molecular theory. Okay. Then the last one is saying at high pressure, molecules are forced closer together. Okay. So this one is not a kinetic molecular theory. So that's the answer. Okay. So that one is talking about the real gas behavior. Okay. So it's not a kinetic molecular theory. Okay. So there the answer is D. Okay. So let's go to part 10. So they're saying amongst these elements, you have your potassium, calcium. Okay, so you have two elements, potassium and calcium, which will have the greater activation energy one or ionization energy one. Sorry, okay. Also ionization energy two and electron affinity. Okay, so which one will have greater first ionization energy? Okay, so let me do this. Let me come up with the electron configuration for potassium. I'll use the condensed electronic configuration. I have my argon there. Okay, so for potassium, the electron configuration for potassium. So these argon indicates the co-electrons for my potassium. Okay, then it will have the 4s1 in the outer. Okay, so this is for my potassium. Okay, for the other guy, which is the calcium. Okay, the electron configuration, I'll still use argon to indicate my co-electrons, meaning I have in the 4s, I have two electrons there. Okay, so now between these two, which one has greater ionization energy? Okay, so you have these electrons which are paired in the s orbital and these electrons which are not paired in the s orbital. So which one has greater ionization energy? So ionization energy is the energy required for you to remove the first electron in an orbital. So that's first ionization energy. So the energy you need to remove an electron from an orbital. Okay. So here you can see that this electron, which is just alone, it's easy to remove it compared to these electrons which are paired here in the s orbital. Okay. So in terms of the first ionization energy, so you need a lot of energy in calcium compared to potassium in terms of the first ionization energy. Okay. Then let's go to the second part, which is the second ionization energy. So we assume we've removed an electron there. So we are remaining with 0 electron in the s orbital for potassium. Also here we've removed 1 electron here for calcium. Okay, so meaning we are remaining with 1 electron. So now the second electron, so the energy needed to remove the second electron from an orbital, that's the second ionization energy. So you notice that for this one, the electrons are now co-electrons. So meaning you are done with the valence electron. So you target the co-electrons, which will require a very big amount of energy for you to remove those electrons. Unlike this one, which is still in the valence electron, which can be easily removed. Okay. So in terms of the second ionization energy, which is the E2, you need a lot of energy to remove an electron. It's the second electron from potassium compared to calcium. Okay. Then the last part, okay, which is electron affinity. Okay, so So electron affinity is how much an electron is attracted to the nucleus. Okay. So if you have a periodic table, as you are moving from your left to your right, electron affinity increases. Okay. So which one has greater electron affinity? Okay, so you notice that potassium is more on the left compared to calcium. Okay, so calcium has greater electron affinity compared to potassium. Okay, so now let's conclude. Okay, so let's arrange them. So in terms of test ionization energy, the greater one will be calcium. In terms of second ionization energy, the greater one will be potassium. In terms of uh, electron affinity, the greater one will be calcium. Okay, so this is your answer. Okay, so if you check here, which one is your answer? Okay, so part A is your answer there. Okay, so part A is your answer. Okay, so you have calcium, potassium, and calcium. Okay, so that's your answer there. Okay, so we go to question number 11. Okay, so we have question number 11 there. They say, under conditions of fixed temperature and amount of gas, Boyle's law requires that. So what is Boyle's law? Okay, so Boyle's law says that when the pressure is inversely proportional to the volume, okay, so the pressure is inversely proportional to the volume at a fixed temperature. Okay, so at a fixed temperature, the pressure will be inversely proportional to your volume. So meaning your P1 V1 will be equal to constant. So your P1 V1 is always constant. Okay. Okay. Also your P1 V1 is equal to P2 V2. That's what this means. Okay. So is constant. So P1 V1 will be always be equal to your P2 V2. Okay. So meaning can also have my P1 P2, okay, so should be equal to, so I'm just changing this here. I can also write this in this way. So P1 divided by P2 is equal to V2 divided by P1, okay, so it's the same thing, okay. So here is the same thing, okay, divided by V1. So you cross multiply there, you are still getting this equation here. So this is the same thing. So all these equations are Boyle's law. Okay. So your answer there is D. Okay. Let's go to question number 12. Okay. So we'll go to question 12. So question number 12, same. The volume of your sample. Okay. So the volume of a sample of nitrogen is 6 liters. Okay, so being given the volume of your sample nitrogen to be 6 liters at 5 degrees Celsius and the pressure of 740 torr. So what is the volume? What volume will it occupy at standard room temperature and pressure? Okay, so what volume will it occupy standard room temperature and pressure? Okay, so here we combine the gas laws. Okay, so combined gas laws. So what are we going to get? Okay, so you have your P1 V1 divided by T1 is equal to your P2 P2 divided by T2. So now what are we looking for? We are looking at for the volume at which this gas will occupy at room temperature and pressure. Okay, so meaning we have to make volume subject to the formula here. So which is the V2. Okay, so we have to make this guy subject to the formula. So what are we going to get? So we will make the V2 subject to the formula. We simply move these guys the other side. Okay, so if I move these guys the other side, I'm simply multiplying by okay, so multiply both sides by T over T2 over P2. Okay, so meaning I'll get, okay, so I'll get an equation which looks like this. So my V2 is equal to, okay, so I've multiplied this side by T2, okay, so T2 will be on top, okay, so meaning I'm having T2, okay, also V1 and P1 on top, okay, then down I'll have my, so I've multiplied both sides by T2 over P2 so that these guys cancel, okay? So whatever I do the other side, I do the same within this side, okay? So T2 over P2, okay? So I have divided by P2 V T1 there, okay? So I'll remain T1 there. So T1. So I've just made the V subject to the formula there, okay? So from there, I can calculate my V2 there, okay? So I simply put whatever I'm having, okay? So what's the temperature? What's the second temperature? Okay? What's the two I'm having? Okay? So the second temperature I'm having, it's 35 degrees Celsius. Okay? So we're having 35 degrees Celsius, which is this is my temperature 1, 8. Okay? So this will be at standard temperature. Okay? So for the standard temperature, you know, my T2 is going to be my 273, okay, Kelvin, okay. Then times, okay, the volume there, okay. So the volume one, the first volume is 6 liters, okay. I have my 6 times. Then the first pressure, okay, the pressure, which is this 740 toe, okay. So I have my 740 toe, okay. So this 740 toe, okay. So this 740 toe, okay. So I simply multiply with my my pressure there, which is 740, okay. 740 okay, then divided by, okay, then we have the second pressure, okay, the second pressure, okay. So at one at a standard room temperature and pressure, so the pressure, the P2 will be 1 atmosphere, okay. Then the temperature will be the temperature one is the one being given, which is 35 degrees Celsius. So we convert it to Kelvin, which will be 308 Kelvin. Okay, so I divide there. I'm going to get my final answer to be 5.18 liters. Okay, so here the answer is E. Okay, so that's what I'm having. Okay, so I can simply move to the next question, which is part 13. Okay, so question 13. So I have my question 13 there, which is saying, what is the density of ammonia gas at 2 atmosphere pressure and a temperature of 25 degrees Celsius? Okay, so being given the pressure of the gas, which is 2 atmosphere, and the temperature, which is 25 degrees Celsius. Okay, so here from my ideal gas equation, I know PV is equal to number of moles times RT. Okay, so this is from the ideal gas equation, right? Okay, and I know the number of moles are given by, so I can also say this is also equal to the number of moles. I know it's mass divided by molar mass, okay, divided by molar mass, okay. Then I have my RT, which is the same thing, okay. So this is also the same as I have my mass divided by volume, which is density, okay. So, you know, in this case, density is going to be given by pressure, okay. So I have pressure, okay, times my molar mass, okay, divided by RT. Okay, so that's what I'm having. Okay, so if I try to convert this into density, okay, so I'm having this equation. which is density, is given by pressure times molar mass divided by RT. Okay, so what am I having? Okay, so I've been given the pressure, which is 2 atmosphere. I've also I know the mixture for ammonia gas. Okay, I can get the mixture for ammonia gas, and have been given, I know the rate constant, and I've been given the certain temperature. So that one I can now calculate there. Okay, so the pressure I've been given is 2 atmosphere. So I have my 2 times the molar mass for my ammonia. Okay, so ammonia simply NH3. Okay, so I get the molar mass for this guy. So 17.03. Okay, then I divide by, okay, the rate constant, which is 0.0821, okay, times the standard temperature, which is 25 degrees Celsius, also 298 Kelvin. Okay, so I get my 2 times 17.03, then I divide by the product of 0.0821 by 298. Okay, so I'm getting my density to be 1.39 grams per liter. Okay, so meaning the answer there I'm getting. Okay, so for this one, the answer I'll get is C there. Okay, so let's go to question number 40. Okay, so so my question number 14 is saying a sample of oxygen occupies 47.2 liters. So I have 47.2 liters under pressure of 1240 torr, okay, at 25 degrees Celsius. What volume would you it occupy at 25 degrees Celsius if the pressure were decreased to 730 torr? Okay, so we are looking for the volume at which it will occupy if the temperature was the pressure was decreased to 730 torr. Okay, so here we know that we are looking for volume. Okay, so you know that from the Boyle's law, you can apply the Boyle's law. So you know that P1 V1 is equal to P2 V2. Okay, so what we are looking for is the second volume. So you can make V2 subject to the formula. So we have P1 V1 divided by P2 there. Okay, so my P1, so I've been given the P1 there, which is the first pressure, which is 1240. Okay, okay, times the volume, the first volume is 47.2 liters. Okay, then divided by the second pressure. Okay, so I've been given the second pressure there, which is 732. Okay, so from there I can find my volume. Okay, so the volume there will be 80.2 liters. Okay, so my answer is E there. Okay, so I can proceed to the next question, which is question number 15. Okay, so question number 15 is saying a 0.58 gram sample of a compound containing only carbon, so it has carbon, hydrogen. Okay, so this sample contains 0.48 grams of carbon and 0.1 gram of hydrogen. Okay, so this sample is only having carbon and hydrogen, and the volume, the mass for carbon is 0.48, and the mass for hydrogen is 0.1. Okay, at standard room temperature and pressure, so we have 33.6 milliliter of a gas has a mass of this one, okay, which is 0.087 grams. Okay, so what is the molar formula for the compound. So we are looking for the molar formula for the compound. Okay. So you know that for the molar formula, for you to get the molar formula, you need to get the empirical formula. So you get the empirical formula. So you always get the empirical formula, then you multiply by n. And you know how to get the n. So you get the molar mass of your molecular formula divided by molar mass of your empirical formula. Then you get your n. Then you multiply times the empirical formula. Okay. So let's follow those steps. Let's get the empirical formula first. Okay. So I have two compounds here. Okay. So let me make a table, simple table here. So how do I get my empirical formula? So when I get it, I'll put it there. Okay. So how do I get my empirical formula? So I follow these steps. Okay. So I know for me to get my empirical formula, I need the number of moles. Okay. And I know the formula for my number of moles. So number of moles is given by, okay, so number of moles is equal to mass divided by molar mass. Okay. So for me to get my number of moles, so I have my elements which are carbon and hydrogen. For me to get the number of moles, I'll need these things. Okay. So I'll need the mass. Okay. So I'll need my mass. I also need my molar mass. Okay. So then from here I can calculate my my number of moles there. Okay. When I have my mass and my molar mass, I can simply apply the formula for number of moles to get the number of moles. When I get the number of moles, what do I do next? So I'll divide by the smallest. Okay. So I'll divide by small. When I divide by smallest, I'll multiply by a certain factor. So the factor multiply by a certain factor. So the reason why I'll be multiplying with a certain factor is to make sure that I have numbers which are closer to the whole number. Okay, so let's do that. Let's start with the masses. We've been given the masses for carbon, which is 0.48, okay, grams. Okay, so this mass is in grams. Okay, then this is grams per mole. Okay, so I have my mass in grams, okay, which is 0.48, okay. Then for hydrogen, I have 0.1 grams, okay. Then the molar mass for carbon, it's 12.01. For hydrogen, which is 1.008, okay, grams per mole, okay. So you can calculate the number of moles. For carbon, I get my 0.48 divided by 12.01. I'm going to get 0.04 moles. Okay, so this is the number of moles in moles. Okay, then for hydrogen, I get my 0.1 divided by 1.008. I'll get 0.099. Okay, so here I'll divide with the smallest. The smallest is 0.04. So I divide 0.04 by 0.04. I'll get 1. I get my 0.099 by 0.0004. I'll get my 2 point. So if I get 0.099 by 0.04, I'll get this number here, which is 2.475. Okay, as my number of moles there when I divide with the smallest. So I'm simply dividing with 0.04 because the smallest number. So I divide everywhere with that number. Okay, so if I divide that number with 0.04, I'll get 1. I'll divide that number with 0.099, I'll get this number. Okay, now this number is not closer to a whole number. Okay, so what do I do for me to multiply with it? To make it a whole number? I'll start doing trial and error. Okay, so I'll get in the whole numbers. When I multiply with that whole numbers, I'll check if it's giving me a number closer to a whole number. Okay, so if I multiply with a 1, I'm going to get the same, so it's not helping. I go to 2. If I multiply with a 2, carbon there, I'll get a 2. Then this one, if I multiply with a 2, okay, so I get my 2 point, okay, so let me take okay. So I get my 2.475, okay, I multiply by 2, okay, so I'm getting 4.95. Okay, so this 4.95 is closer to a whole number. It can easily be rounded off to 5. So can easily round off that number to 5. Okay, so meaning my empirical formula now using these ratios is, so on the on C I have 2. Okay, so I have C2, then H5. This is my empirical formula. So now what I need to do is to look for N. Immediately when I find N, I can find the molecular formula for this question. Okay, so how do I get my N? Okay, so I know for me to get my N, I need the molecular formula for this empirical formula. Okay, so I need them molecular mass. We haven't been given the molecular mass for the molecular formula. Okay, so in this case, what do I do? Okay, so I use the ideal gas equation to come up with the number of moles. Okay, those number of moles are going to help me to come up with the mass for my a true molecular formula. Okay, so I know that molecular formula, okay, molecular formula is given by mass divided by number of moles. Okay, from the information I've been given, I can use the ideal gas equation to come up with the number of moles. Okay, then I've been given the mass of the true solution, or true the mass of the true solution or molecule, okay, which is 0.087 there. Okay, so what I can do, I can come up with the number of moles. Okay, so I have the true mass. Okay, so all I need is the number of moles. So how do I get the number of moles? I use the ideal gas equation. Okay, so I know PV is equal to nRT. Okay, so I make N subject to the formula here. So I have N is equal to PV divided by RT. Okay, so the pressure being given, the pressure at standard temperature, okay, which is 1 atmosphere. Okay, so this the pressure at standard temperature and pressure is 1 atmosphere. Okay, times the volume. Okay, so the volume I've been given is 3.6 milliliter. Okay, now if I check my rate constant is in liters, so I'll need to change that milliliter to liters. Okay, so how do I change my milliliters to liters? I'll divide by 1000. So I divide 33.6 by 1000. I'm going to get 0.0336 liters. Okay, then divided by the rate constant. Okay, rate constant, which is 0.0821. Okay, times the temperature. Okay, so the temperature at 25 degrees Celsius, which is at standard room temperature and pressure, which is 273. Okay, so there I'll get my number of moles. Okay, so the number of moles there will be 0. Okay, so I get my 1 times 0.0336, which is 0.0336. Okay, divide by the product of 0.821 by 273. I'm going to get 0.0015 moles. Okay, so these are the number of moles. So now I can put my number of moles there. Okay, I found my number of moles. I can simply put them on the formula. Okay, so I have my formula here. The mass I've been given is there, which is 0.087 grams. Okay, so this is the mass of my molecular formula. Okay, then divided by then the N, which is 0. The number of moles, 0.0015 moles. Okay, so we can calculate the mixture for my molecular formula there. So the mixture for my molecular formula is going to be, so I divide these two. Okay, I'm going to get 58. Okay, so 58 grams per mole as my molecular formula. So I have my the molar mass of my molecular formula. So I can find the value of N to replace there. Okay, so I get the mass of my molecular formula divided by the molar mass of, so these are the molar masses of my empirical formula. Okay, so this, okay, so the molar mass for my molecular formula I've already found, which is 58 grams per mole, divided by the molar mass of my empirical formula. So I have two terms, so this is the empirical formula. So I get my two terms, 4.01 plus my 5 times 1.008. Okay, so there I'm going to get 29. Okay, so I get 29 grams per mole. Okay, so I divide these two. So I'm going to find the value of n. Okay, so my value of n there when I divide the two is going to be 2. Okay, so my value of n is equal to 2. So I can simply paste a 2 there. So my molecular formula is going to be C4H10. Okay, so which is D there. Okay. Okay. So I can go to part 16, question number 16. So I can go to question number 16 there. Okay. Okay. So question number 16 is saying, consider the species. Okay. So you have zinc. Okay. So you have zinc with the mass number of 72. Then you have AS with the mass number of 75 and GE with the mass number of 74. So now these species do they have the same electron number of electrons? No. Okay, so they don't have the same number of electrons. Okay. Then do they have the same number of protons? No. Okay, they don't have the same number of protons. Okay. Do you have the same number of neutrons? No. So if they don't have the same mass numbers and proton numbers, meaning the neutron numbers are not going to be the same. Okay. Then do you have the same, let's see, the same proton and neutron numbers, which is also false. Okay. Then they have the same mass numbers, which is also false. Okay. So there, all the choices they are false. Okay. So all the choices here, they are false. So you don't have a correct answer there. Okay. So you don't have a correct answer here. But on question number 16, you don't have a correct answer there. Okay. So we can go to the next one, which is question number 17. Okay. So it's saying, what is the atomic weight of hypothetical element consisting of isotopes 1 with the mass of say 64.23, then atomic mass unit and the percentage abundance will be given there, and the other one with a mass of 65.32. Okay, so definitely this one, if the percentage abundance, if these isotopes are only 2 and the percentage abundance for this one is 26%, meaning the percentage abundance for the other one 74%. Okay, so now they're asking to calculate the atomic weight. Okay, so atomic weight in that case be given by, so you get the percent abundance, okay, times the atomic mass number. Okay, so atomic mass, okay, plus for isotope 1. Okay, we do the same with isotope 2, the percentage abundance times atomic mass. Okay, so you get the summation there. Okay, so the percentage abundance for the first one, so you have 26/100 times the relative atomic mass number, which is 64.23, okay, plus Second one, the percentage abundance 74 divided by 100 times atomic mass number, which is 65.82. Okay, so there, when you do your calculation, so you divide there, you're getting 0.26 times your 64.23. Okay, then you add here, you're getting 0.74 times 65.32. Okay, so you multiply these two and add them, you're going to get the the average atomic mass number of 65.04 atomic mass unit. Okay, so which is this one here. Okay, which is 65. Okay, so we can go to question number 18. Okay, so question number 18 saying what is the frequency of a light having a wavelength of 4.50 times 10 to the power 6 centimeters. Okay, so being given the wavelength, now we are being asked to calculate the frequency. Okay, so you know that frequency indicated by delta V is equal to, you get your speed of light divided by lambda. Okay, so this lambda is the wavelength. Okay, so the speed of light, I'll use 3 times 10 to the power 8 minutes per second. This is the speed divided by the wavelength. So we've been given the wavelength to be 4.50 times 10 to the power negative 6 centimeter. So this is in meters, this is in centimeters. You can change your units there from centimeters to meters by simply multiplying with the conversion factor. I know 1 meter is giving me, so I know 1 meter there is giving me, okay, so I can have 10 to the power negative 2 meters giving me 1 centimeter, okay, as a conversion factor, so that the centimeters and the centimeters will go. Okay, so I have this here, so I have 2 times 10 to the power 8 meters per second divided by, so now I have 4.5 times 10 to the power negative 8 now meters. Okay, so that the meters and the meters will go, so we only remain with the second. Okay, so you divide these two, you're going to get so you get your 3 divided by 4.5. Okay, so here you will get your final answer to be 6.67 times 10 to the power 15 per second. Okay, or hertz. Okay, that's your final frequency. Okay, which is E there. Okay, so we can go to question number 19. So question number 19 is saying the emission spectra of gold shows a line of wavelength 2.676 times 10 to the power negative 7 meters. How much energy is emitted as the excited electron falls to the lower energy level? Okay, so here you have been asked to calculate the energy. So energy is given by h, which is the Planck's constant, c, the speed of light, divided by wavelength. So you are able to find energy there. Okay, Planck's constant, 6.626 times 10 to the power negative 34. Sorry, okay. Then times the speed of light, which is 3 times 10 to the power 8 meters per second. Okay, then divided by the wavelength being given, which is 2.676 times 10 to the power negative 7 meters there. Okay, so we divide those two. Okay, you're going to get, okay, your energy to be 7.43 times 10 to the power negative 19 joules. Okay, so this is your energy. Okay, so the answer there is A. Okay, so let's do the last question and call it a day. So last question is saying the Heisenberg principle states that, so the Heisenberg principle states that A, so no electron in the same atom can have the same set of 4 quantum numbers. Okay, so that one is what we call a Pauli exclusion principle. Okay, so Pauli exclusion principle states that you can't have electrons, okay, in the same atom having the same 4 quantum numbers. Okay, so this one is Pauli, so it's not Heisenberg uncertainty principle. This is Pauli exclusion principle. Okay, so we cancel this out. Okay, we go to 2. Okay, 2 same 2 atoms of the same element must have the same number of protons. Okay, so this has nothing to do with the Heisenberg principle. Okay, we go to 6. It is impossible to determine accurate both the position and the momentum of an electron simultaneously. Okay, so let's see there. Heisenberg principle is the one. Heisenberg is the one who came up with this idea, saying, okay, we don't really know where an electron is located. Okay, so we can't really tell the exact location of an electron. Okay, so this one, which is saying it is impossible to determine the accurate both the position and the momentum of an electron simultaneously. So this is the Heisenberg principle. Okay, then this one, electron of an atom in their ground state enter energetically equivalent sets of orbital singly before they appeared up in any orbital of the same set. Okay, so that's Hind's law. Okay, so the Hind's law. Okay, then the last one, the charged atoms must generate a magnetic field when they are in motion. So this has nothing to do with the Heisenberg principle. So here the Heisenberg principle is C there. Okay, so we are done with this paper. Okay, so what I'll do, I'll also solve part B and C. So for you to be part of those solutions, you need to register with us. So you register with us by using the link in the description provided. Once you register, you should be able to access our website. So you create an account using that link in the description. When you create an account, you should be able to access our website as well. You can also download our website you can download the app on Play Store. It's there. Okay. Once you download, you should be able to access more videos and live classes like this one. Okay. Thank you so much.